So far we have covered some basic mathematical tools useful for microeconomic analysis, namely differential calculus, partial differentiation and unconstrained and constraint optimization problems. Now it is time to look at some exercises as illustration, so that the idea of partial differentiation and optimization becomes clear to you. Now we are going to discuss two illustrations, one on unconstrained optimization and other one on constraint optimization. We will start with a problem on unconstrained optimization. Let us think about a maximization problem where the function is defined over two variables x1 and x2, and this is the form of the function. So, let us assume a functional form and of course, the decision variables are x1 and x2. So, this is an unconstrained problem. So, the first step would be to take the first order derivatives in order to form the first order conditions. So, f1 will be 70 minus 2x1 and we have to set that equal to 0. Then the second first order condition will be with respect partial derivative of function with respect to the variable x2, and that will be equal to 90 minus 3 x2. We have to set that to equal to 0. Now, of course, there are two decision variables to solve and two equations. So, we can get the solution x1 star equal to 35 and x2 star equal to 30. Now, this is the first order condition and this is the solution to the problem, but we have to test whether this is giving indeed a maxima or a minima. So, now we have to look for the second order condition. Now, second order condition will depend on the higher order partials, right. So, we need to now construct f11 and that will be minus 2, then we need f22 that will be equal to minus 3, then we need f12 and we know that that will be equal to f201 and that equals to 0. And then the next step would be to set up the Hessian matrix. Right. So, the Hessian will take the form minus 2 0 0 minus 3, and then we need to evaluate the determinant of the Hessian matrix, and we need to evaluate that at x1 star x2 star, right. So, if we do so, then we get the Hessian as minus 2 times minus 3 minus 0, and that is equal to 6, that is greater than equal to 0. So, we see the determinant value is a positive one. Then let us also note that f11 is equal to minus 2, which is less than 0. So, thus we can infer that the optimal solution gives a maxima. Now, we are going to look at a constraint maximization problem. Now, we are going to assume a power function, because power functions are very common in microeconomic analysis, and I hope that an example or illustration with respect to the power function will help you in this course. Here I am going to assume a function again defined over two variables x1 and x2 as x1 square and x2 cube. Now, we want to maximize this function f subject to a constraint 7x1 plus 5x2 equal to 105. Now, if we have a power function, it is convenient to express that power function in a log form, because logarithm is a monotonic transformation, it will not change our solution. So, let us take log and we get log of x1 equal to 2 log So, we are going to maximize log fx in place of fx. So, by nature this is a constraint optimization problem. And we can set Lagrangian equal to 2 log x1 plus 3 log x2 plus we have this Lagrange multiplier lambda So, now we know that we need to differentiate the Lagrangian function with respect to 3 variables, 2 decision or control variables x1 and x2 and the Lagrange multiplier lambda. So, let us do this one by one. So, first we take differentiation with respect to the variable x1. We get our first order condition. Then we differentiate the Lagrangian, partially differentiate with respect to the control variable x2, and that will give me my second first order condition. And then finally, I have to again differentiate the Lagrangian with respect to this time the Lagrange multiplier variable, and that would give me basically the constraint. Now, there are 3 variables, control variables or decision variables, and 3 equations. So, of course, we can find solution to this set of equations, and if we find out solution, we can get these values x1 star equal to 6, x2 star equal to 12.6 and lambda star equal to minus 1/21. It's a very small number. I am skipping the steps. Now, whether this set of values x1 star, x2 star and lambda star indeed give maxima or not, for that we have to check the second order condition, right. So, now we are going to look at the second order condition. So, in the second order condition we know that we have to use the concept of bordered Hessian, right. So, the elements of the bordered Hessian will come from the higher order partials. So, let us first construct them one by one. And finally, so we can now construct our bordered Hessian. And it will take the following shape. Zero, 7, 5, 7, 5. I am writing the bordered elements first. Right. So, the border element is basically so this gives you the border and this one as well. So we get Hessian matrix evaluated at the optimal solution x1 star, x2 star and lambda star to get a new H matrix 0, 7, 5, 7, 5 minus 1/18, 0, 0 minus 3, 12.6 square. Note that I am not interested in deriving the particular values, because actually we do not need to derive the particular value of the determinant of the bordered Hessian. What we need to see? We need to look at the sign and we can judge from the sign. So, this matrix will lead to this particular determinant . And we can see here that the sign of the determinant will be a positive one. We do not have to calculate the values of the determinants, we need to see the sign of the left hand side determinant and we get a positive sign of the bordered Hessian determinant, and we can then say that x1 star, x2 star and lambda star indeed generate or give a maxima to this optimization problem. So, with these illustrations our discussion on basic mathematical tools are done. Now, we are going to start the modern consumer theory and we will start with the Hicks-Allen indifference curve approach or ordinal utility approach in the next lecture.